Cosmology has changed forever with the launch of the James Webb Space Telescope on Christmas Day 2021. Since then, it has opened its impressively sharp, high-resolution infrared eyes to look back at some of the earlier stages of the universe. James Webb has gathered sharp, pristine, and beautiful insights into early star and galaxy formation. It has provided crucial information about the formation of planetary systems, including our own solar system. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some of these infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise, a plethora of seemingly impossible early galaxies. Even at these earliest times, these galaxies were too big, bright, and numerous to explain. Some of them appeared even older than the universe according to our best models based on the lambda cold dark matter model, the standard model of cosmology. The discoveries made by James Webb could shake our understanding of galactic history. So is the Big Bang and all of modern cosmology in trouble? Join us as we dig deep into how James Webb just found massive structures that could defy our current theories of the universe. The further back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxies. Their number density should rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and protogalaxies, which should be extremely blue and primitive, existing in low number densities. Finally, there should truly be a time where the very first stars and star clusters have all appeared. Beyond that, there should be no luminous sources at all to observe except for the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we're basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope and with its spectroscopic capabilities in particular allows us to test that model. It helps us see if we truly understand the universe we inhabit, or if every year we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena. Its greatest scientific contribution might be its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb's Cosmic Evolution Early Release Science Survey are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies dating back as much as just a few 100 million years after the Big Bang, they found far more of these galaxies than anyone had predicted. According to Ma Bagley of the University of Texas, one of the leading researchers in the Cosmic Evolution Early Release Science Survey, the theoretical models didn't predict that these should be there. We still don't yet know how you can see a galaxy that bright that early. One particular galaxy jumped out of the survey data straight away, Mace's Galaxy, named after the daughter of Stephen Finkelstein, one of the researchers. Mace's Galaxy is 13 billion years old, making it one of the oldest galaxies ever observed. It is much brighter and much bluer than anyone predicted. As Bagley said when they found Mace's Galaxy, the surprising part was, how is it in the universe? It's exciting because this is the universe we live in, a universe with a ton more galaxies than we thought. Webb is able to detect extremely distant galaxies because its instruments operate in the infrared wavelength. A small handful of extremely distant galaxies had been detected previously by the Hubble Space Telescope, which operates primarily in the optical light wavelength, equivalent to what human eyes can see. However, as galaxies move further and further away from us due to the expansion of the universe, their light is shifted toward the red end of the spectrum in a process called redshift. The extremely distant galaxies that early universe researchers are interested in have light that is shifted so far that it is no longer visible in the optical and can only be seen in the infrared. Hubble's instruments were pushed to the limits to detect even a few of these galaxies, while Webb was able to detect many of them incredibly quickly, within a few days of the telescope beginning its science operations. When discussing these galaxies, scientists typically talk about them in terms of their age rather than their distance. You'll see researchers describe a galaxy as being from the first few 100 million years after the Big Bang rather than being located billions of miles from Earth. That's also because of the expansion of the universe, which creates a moving frame of reference that makes it hard to describe distance meaningfully. Examples include galaxies like Mace's galaxy, which is described as being 13 billion years old. The light has traveled 13 billion years to get to us, but if we could see Mace's galaxy today, it is much, much further away because in that time the universe has kept expanding and accelerated its expansion. The time the light has spent traveling to us gives us more concrete information about when in the universe we're observing these galaxies. Initial estimations of the redshift and thus age of Mace's galaxy were based on photometry, which works by analyzing brightness in images while using a small number of wide-frequency filters. These calculations suggested the galaxy had a redshift of 11.8, but Finkelstein and the Sears team wanted a more accurate age estimation. To do this, they made follow-up observations with James Webb's Near-Infrared Spectrograph, or NIRSpec for short. This allowed Finkelstein and colleagues to look at spectral lines created in light data dictated by the absorptions and emissions of chemical elements at specific wavelengths. From there, they could pinpoint the actual redshift of Mace's galaxy. It appeared to be 11.4. This means Mace's galaxy is technically seen more recently in the universe than initially estimated by a factor of tens of millions of years. Nonetheless, it is still considered immensely old. James Webb captured the galaxy as it was just 390 million years after the Big Bang. This impressive age places Mace's galaxy among the four oldest galaxies in the universe that have had their ages confirmed by spectroscopy, a technique that splits light into its component frequencies to better reveal its brightness, heat, and chemical composition. While such galaxies don't yet pose problems for leading models of cosmology, they suggest galactic formation began earlier and proceeded faster than expected in the universe, which theorists had previously predicted began churning out galaxies at the ripe age
of 1 billion years after the Big Bang. As Fabio Pucci of the Harvard-Smithsonian Center for Astrophysics said, "We're seeing a rise of massive galaxies faster than we thought previously. The ages of some of these early galaxies are estimated at just tens of millions of years. This could have implications for large structures of dark matter, known as halos, that sculpted early galaxies. The nature of dark matter particles themselves is one of the big open questions. As Sandro Tacchella of the University of Cambridge points out, the first generation of galaxies is a sensitive probe for different dark matter models. On the other hand, we should be cautious, as some problematic and potentially model-busting early universe candidate galaxies still remain. Scientists had already produced models of what early galaxies would be like, and Webb contradicted them almost immediately. As soon as James Webb began looking for early galaxies, it found far more of them than anyone had predicted, and found that they were much brighter too. Light is a double-edged sword in the context of these galaxies. It's what lets us study the galaxies, but there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass because a galaxy's light comes from stars. If you assume a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. However, much of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. According to Jorge Moreno, an associate professor of astronomy at Pomona College, we didn't expect to see so many bright, massive galaxies. If these galaxies are really that massive, then we would challenge our cosmological models. It could be that these galaxies aren't as massive as they appear. Instead, their brightness might be due to the presence of a large number of very massive stars. These would be much bigger and brighter than the stars we typically see today, but this is also a problem. According to David Spergel, the president of the Simons Foundation and the co-chair of the NASA Astrophysics Advisory Committee, it would be a surprise to find such massive, high-density stars at these redshifts. It could be that the galaxies Webb found are producing a massive amount of light due to a process called gravitational lensing. In gravitational lensing, a massive foreground object causes light from a background object to be magnified and distorted. It could be that there are massive foreground objects boosting the brightness of these early galaxies, But this seems less likely to be the whole story. David Spergel goes on to say, if you find them everywhere, then the statistics make it more unlikely that lensing is the answer. If these galaxies are massive and there really are a lot of them, then something would have to change about the early universe. Models of how galaxies form would need to change to accommodate them. It could be that something is happening to speed up galaxy formation, or there might be more matter in these galaxies than previously believed, in which case it might be time to go back to the drawing board for dark matter models. So much of the evidence we have for dark matter comes from the structure and growth of galaxies, and we use our models of dark matter to predict the growth of galaxies. If those predictions don't match reality, our understanding of dark matter might need an overhaul. It's possible that the dark matter component is not exactly what we think it is. This is a massive problem for astronomers. Moreno says that, if we throw away our current understanding of cosmology, it's a big deal. In that sense, Webb might cause one of the biggest shifts in cosmology since Edwin Hubble discovered the universe was expanding. The good news is that astronomers will continue studying these early galaxies with Webb for a long time. This initial unexpected result has led to further proposals to keep looking at these galaxies and gather more data about them. One of the exciting things about James Webb is that we've had so little time with it so far, and it's already delivered surprises. We are truly at the beginning of a new era in astronomy. As David Spergel put it, this is the very beginning of the story.